Today we're going to talk first about stress and strain. So, starting about stress in particular, there are two types of stresses that are typically observed in MEMS devices, normal stresses and shear stresses. So we're going to define stress to be the intensity of internal forces within a body due to loading. Spell loading. So first we're going to talk about normal stress. So I'm going to attempt to draw a picture here. So this will be my z-axis. This will be my x-axis. And this will be my y-axis. And let's say that I have a beam. Okay. Like so. And let's give this beam some dimensions. Okay. So let's say that our beam has some particular length, lowercase l, some particular height, which we'll call h, and some particular width, which we'll call w, like so. And we are going to apply a normal force to this surface such that our force is in the x direction. And if we assume that our beam is anchored to the YZ plane, we should see also an equal and opposite force. That's not where that arrow should go. Over here, okay? So I'm going to define the cross-sectional area of this guy like so. If I could draw something like that. And the vector representation of this cross-sectional area would be in the x direction as well. Okay. So our average normal stress is the magnitude of the applied force over a transverse cross-sectional area. So just to be clear, what I mean by a transverse cross-sectional area, the area itself needs to be orthogonal to the force, or the vector representation of the area should be in the same direction of the force, since the vector representation of an area is orthogonal to the surface of the area, right? So this is exactly the situation that we have. So mathematically, this relationship is going to look like this. So I'm going to call this TXX, where T is what I'm going to use for stress. The reason why I'm using capital T for stress is because I'm going to use the symbol lowercase sigma, which is normally used for stress, to represent electrical conductance in this course. And so we don't have too many things having the same symbols. I'm just going to put a note here. This is what we're using for stress in this class. And so this is simply going to be the ratio of the force divided by the area. Okay. So in general, the normal, goodness gracious, I can't spell, stress at any given point in a transverse cross section of a loaded beam will not equal the average normal stress. So all I mean by this specifically is that if we were to pick any given point in our cross-sectional area or the surface bounded by our cross-sectional area, we probably wouldn't see the average stress, but if we combine all of that together, that's what we're going to get, right? So typically speaking, I think the stresses towards the middle of the cross-sectional area will be larger, and it'll be a distribution that gets smaller and smaller as we go out towards the edges, right? Okay, so now let's consider a beam loaded differently, okay? So all we're gonna do is I'm gonna redraw my shitty beam here. Like, so we're gonna assume it has the same dimensions as we had earlier, so I'm not gonna bother writing those down once again. And instead of applying my force to the center of this face, I'm going to apply it up here. What color did I use for force? Black, okay. So here's our applied force, F of X. This is the force acting on the boundary of our system. And so now this force is acting in a plane where the vector representation of this area of the plane is perpendicular to the direction of the applied force. So effectively, our force, excuse me, our area would be this guy right here, which I'm going to call AZ, like so. So this situation is illustrating shearing force, where we're going to define the shearing stress, where we're going to define the average shearing stress is the magnitude of the applied force to an in-plane cross-sectional area. And mathematically, this is given by the relationship. So in this case, our area is in the z direction, our force is in the x direction. So those are where those subscripts are coming from. So we're going to have f of x over az, like so. And I have a note here that shearing stress is not uniformly distributed over the area that the force is applied to. So those are the two types of stresses that we are most likely to see. So now we're okay. I'm going to switch to a new page and we're going to talk about strain. Were you caught up? Alexia, do you have a question? Sure. All right. So strain is the intensity of deformations caused by applied mechanical stress. So both normal stress and shearing stress will have associated strains, okay? So let's once again redraw my shitty picture of a beam. Once again, the dimensions are going to be completely the same. So I'm not going to bother drawing those. And let's say, once again, for the sake of argument, that in this case, we're applying a normal stress, right? So here's our Fx, okay? So what we would expect to see is that our beam will experience some deformation in the X, Y, and Z directions, okay? So let me just write that down. And I'm going to try to illustrate this. So if we just kind of take a screenshot or snapshot of what's going on, looking at the XZ plane here. So we're going to consider our Y direction is coming straight out of the board at us. Here is our X direction. So if our original outline of our beam, let me just write 3, looks like it's 6 units in total, was something like this, and we applied a large enough force, and this is definitely exaggerated. So let me just write something out here. So this distance is L. We would tend to expect that our beam will get longer. Like so, where this is our applied force, F of X, and this is the vector representation of our cross-sectional area, A of X, like so. And we have some change in length that I'm representing by delta L, okay? So this is what's known as a longitudinal strain. And this is a relative change in length due to applied stress. And mathematically, we're going to call this SXX, where this is our strain, is simply the ratio of delta L over L. If we look at what's going on in the other directions or the other dimensions of our beam, so here's the z-axis, here's the y-axis, and our x-axis is directed out of the plane. Our original dimensions should have been something like this. And what we'll see is that our beam shrinks in both the z direction and the y direction due to our applied force in the x direction. So if this dimension was our original width, and this dimension right here is the change in our width. And similarly, if this direction right here were our change in height, then this dimension right here is our change in height. And so what we have here is a transverse strain, which represents a relative change in the lateral dimensions. Of a body due to an applied stress. And mathematically, we'll have a transverse strain SYY, that is simply the change in width over the nominal width. We'll have a transverse strain SZZ, that is a change in height over the nominal height. And these strains should be approximately equal to each other. So why does this beam under extension experience these 3 strains? Well, effectively, the mass of the beam can't change, right? We can't add or remove material from the beam itself just by trying to make it longer, make it shorter. We can't change the density of the material. That's effectively a material constant. So the only thing that we can really do is effectively change the volume. So if L gets longer, W and H have to get smaller in order to try to maintain a constant volume for our system. And this relationship is described mathematically by Poisson's ratio, okay? So Poisson's ratio is simply trying to remember what that Greek letter is supposed to be. It's the one that looks kind of like a lowercase v. Anybody remember the name of that bad boy? Nu. Okay, nu it is. Nu tells us that negative SYY over SXX needs to be equal to negative SZZ over SXX, where I'm making an assumption here that we are elongating the beam, and so the Y and Z directions are effectively getting smaller. So that's where that negative sign is coming from. Okay. So now let's consider a beam undergoing shearing strain. Okay. So we'd have something like this. Once again, a shitty picture of a beam. Here's our force, f of x. And so if we were to just look at the effects of the strain, and I'll just do that over here, we might have something that looks like this. This is going to be vastly exaggerated, just to be really clear here. So effectively, we're seeing some deformation, and the strain is effectively just, or the shearing strain is just a measure of the change in shape of this body undergoing the deformation, where we would have a shearing strain of SZX is equal to the change in X over the height, where our height, recall, is this dimension. That actually should have been 3 units high, but whatever, you guys get the gist. And then our delta X dimension would have been this guy right here. All right, so stress and strain are closely related to each other by a constant called the modulus of elasticity, okay? Under small deformations, stress and strain are approximately linearly proportional. So for a longitudinal stress, we would have Txx is equal to E, where E is Young's modulus of elasticity multiplied by Sxx. And let me make a note here. And Tzx will be equal to G times Szx, where G is the shearing modulus of elasticity. So Young's modulus of elasticity has units typically of gigapascals, okay? And our shearing modulus of elasticity's units are typically expressed as newtons per meter squared, okay? So Young's modulus quantifies the stiffness of a material, and the shearing modulus of elasticity quantifies the ductility of a material. And these two material constants are related to each other through Poisson's ratio, as G, our shearing modulus of elasticity, is equal to E, our Young's modulus of elasticity, divided by twice 1 plus nu. So I'm going to attempt to draw a graph here depicting the relationship between stress and strain. So if we put stress on this axis and strain on this axis, we might see something like this. Okay, and this is for a generic material. So we should expect to see a linear increase when the strain is low, which we've already kind of mentioned. I'm going to put an X here. And I'm going to subdivide this graph into lots of smaller parts. So this is going to be region 1. This is going to be region 2. This will be region 3. And over here will be region 4. This point right here is what's known as the proportional limit. And then this height right here is what's known as the yield stress. And then everything from here on, so regions 2 and greater, are what are called the plastic regime. And then this point right here is what's known as the fracture point, where the material fails. So region 1 is the elastic region, and it represents where our stress and our strain are linear related, okay? So in this region, if the stress is removed, the material should be expected to return to its original shape, and the force loading can be repeated an infinite number of times without causing permanent deformation, right? Our second region is called the perfect plasticity or yielding region. Okay, actually, I should probably write this shit down, shouldn't I? All right, so region 1, this is the elastic region. And just to summarize, stress and strain, or strain and stress, sorry, I'm getting my symbols mixed up, are linearly related. Material returns to original shape when loading forces are removed. Okay. Region 2 is the perfect plasticity or yielding region. Stress and strain are no longer linearly proportional. And plastic deformation has occurred. In region 3, we have a stress hardening region. Excuse me. So stress increases as the material elongates. Until the ultimate strength point is reached. That's where we're at our maximum right here. And then lastly, we have region 4 is the necking region. And it's called this because beyond the ultimate strength point, a neck forms where the local cross-sectional area becomes smaller than the average cross-sectional area. So local cross-sectional area becomes smaller than average cross-sectional area. And this occurs until the fracture point is reached at which irreversible failure occurs. Okay. And for those of you that had engineering 220 here, you probably actually saw a physical demonstration of this down in ISB 224, I believe, with that machine that literally pulls pieces of metal apart and all that kind of good stuff. So this is our general graph, okay? Now, silicon is a very brittle material. So instead of it having all of these different regions, it effectively just has the elastic region and then a brief-ish dip into the plastic region before failure occurs, okay? So it would look more along something like this. So effectively, we have linear proportionality until it starts to round off, and then we hit our yield stress, and then it breaks. So I'm just going to put SI stress strain curve here, okay? All right, and the last thing that I'm going to hit you guys with before we move on to something different is some constants for silicon specifically. So because silicon is an anisotropic material, which means that different directions have different material constants, I'm going to give you some information. So whenever I put SC like this, that just means single crystalline silicon. So for single crystalline silicon, for the 100 plane, we have a Young's modulus measured in gigapascals of 130. And we have a Poisson's ratio of 0.25. For single crystalline silicon in the 110 family of planes, we have a Young's modulus of 170 and a Poisson's ratio of 0.3. For single crystalline silicon in the 111 family of planes, that's 189 for Young's modulus, 0.36 for Poisson's ratio. And lastly, for polycrystalline silicon, we have 160 for Young's modulus and 0.25 for Poisson's ratio. Okay. So these are our stress, Young's modulus and Poisson's ratio, which we could use to calculate the shearing modulus of elasticity if we needed to, for different types of silicon that are commonly used in the development of microstructures. Okay, so before we get on to something that I find slightly less boring than just a review of stress and strain, does anybody have any questions, comments, or concerns? All right, so let me can I jump to a different page? All right. Now for the arguably fun part. Beams as springs. So when most of us think of a macroscopic spring, we are probably thinking of a coiled section of metal that can elongate, right? Now, that's not the only type of macroscopic spring. You can have stacked sections of curved pieces of metal. Those are called leaf springs. You usually see those in the suspensions of like large 18-wheelers and stuff like that when they're driving by. Well, we can't really fabricate coiled sections of anything through standard CMOS fabrication processes because we are stuck with the boundaries of a planar substrate. So instead, we typically wind up making our springs for our microstructures out of just straight sections of silicon, okay? So there are 4 different types of springs that are commonly utilized in MEMS devices, and we're going to talk about all of them here, kind of bit by bit. So we're going to start with an extension rod spring. And an extension rod spring is quite literally just a beam undergoing normal stress, okay? So if we define this as our Z direction, and these lines here are just representing that this is our anchor point effectively. We're going to define this as our X direction. We learned not too long ago, within the last 20 minutes or so, that I can apply a force actually to a beam like this, and I expect it to get longer. And I am greatly exaggerating the length of this spring getting longer, right? So we could consider this dimension as our nominal length L, this dimension right here as our change in length due to some applied force f of x like so. And once again, I'm just going to denote my cross-sectional area a of x like so here. All right, so we can use the relationship between normal stress and normal strain. So Txx is equal to Young's modulus times Sxx. Txx is F over A. And so this will be equal to the change in length over the nominal length. And from this, we can simply rearrange things really quickly and see that our change in length is then going to be our force times our nominal length divided by Young's modulus times our cross-sectional area. We could also, for what it's worth, rearrange this guy to solve for our force, okay? And the reason why I want to do this will be obvious in a moment. So our force would be Young's modulus times our cross-sectional area times our change in length divided by our nominal length. Okay? Well, the reason why I'm putting it in this particular form is because if I'm going to treat this thing as a spring, I want to make it look like Hooke's law as much as I can so that I can figure out what my spring constant is. Well, Hooke's law is just F is equal to K, our spring constant, times the amount of spring extension, which is what we're calling delta L, right? So I'm going to call this K subscript E, where this is just the spring constant for a beam in extension times delta L. And from this then, KE is E AX over L. For what it's worth here, so Young's modulus has units of typically gigapascals, right? Which is what I would typically associate with pressure. So it's force per unit area. Then we're multiplying by area. So that's just giving us force. And then we're dividing by length. So this is probably going to be expressed in units of newtons per meter or newtons per centimeter, micrometer, et cetera, right? So this is our spring constant for a beam in extension. This is the simplest MEMS spring. And we're going to find that this one, typically speaking, gives us actually the largest spring constant. So it's much harder to extend a piece of silicon than it is to bend it in various directions. Okay. So any questions on the extension rod spring? Hopefully real easy. All right. Less easy is cantilever beam springs. So a cantilever beam spring is one where we have a beam that is undergoing shearing stress, okay? So if this is our Z direction, and once again, I'm going to make the left-hand side an anchor. Here is our X direction. So I'm going to try to draw the profile of the spring prior to cantilever bending. I'm going to draw this one a little skinnier as well. So this is our profile before bending. Then we're going to be applying a shearing force on the end. We're going to assume that we're applying our force direction down. And so what we're going to wind up seeing, and let me put the axis of symmetry here in the middle. And so what we'll be more likely to see now would be something like this. And again, kind of an goodness gracious, exaggerated version of things. But this is our force was applied in the Z direction and caused the tip to displace. We are going to say that this distance, so between the center point of our beam and our original axis of symmetry, that's going to be, let's call it capital Z. Okay. So it's some amount of movement in the Z direction, but I'm trying to distinguish it from lowercase z, the variable. Are we all okay with that level of understanding? And then we're also going to have some angle, theta, telling us how much, or the angle of deflection of the tip of our beam, okay? So unfortunately for a cantilever beam like this, the math is quite a bit harder. So this type of displacement is governed by the following differential equation. E, our Young's modulus, times I, the second moment of inertia in the direction of bending. So let me write that down. Times the second derivative of our displacement. Let me write that as a capital Z as a function of capital X, where X is the location along the beam length divided by, with respect to X squared, is equal to M as a function of position, where this M is the moment of force where this is typically equal to force magnitude multiplied by the distance from the point of rotation. Excuse me. So this expression is what's governing how our beam is behaving, or how our tip is behaving depending on where we applied our force. So one thing that I want to be clear about here, we are deriving all of this such that our force was applied at the very end of our cantilever beam. That doesn't necessarily have to be the case. If we applied it, say, here, right, this would still be considered a shearing force, so we would still have cantilever bending, but effectively the section of material to the right of where we applied our force wouldn't bend. It would just be a straight section, like all of our equations would be related to where we are applying our force, is effectively what I'm getting at. Just want to clarify that. Okay. So since our MEMS springs or beams are usually rectangular, our second moment of inertia, I, will be given as AB cubed over 12, where B is the dimension in the direction of beam bending, and A is the transverse direction of the cross-sectional area. So for what it's worth, if we defined this dimension as our height, that would be B. And then the thickness of the beam extending into or out of the board would be A. And then the length of the beam would be L. Okay. So let me just make a note here. This is L, and then I'm just going to put a note. W is the depth / width of beam into / out of the page. Okay, so let's math this thing up. So we have boundary conditions on this beam, okay? So at the fixed end of the beam, where X is equal to 0, our displacement has to be 0 because we're not allowing it to move. It's anchored to that wall. And we're also not allowing it to rotate, once again, because it is anchored to that wall. So we have some initial conditions. Z at, actually, let me do this as uppercase. So Z at capital X is equal to 0 is 0, and the partial derivative of Z at capital X with respect to X at x equals 0 is also 0. So using these two initial conditions and our second order differential equation, we can actually solve for a function that tells us how our beam is deflecting, right? And so all we're going to do is just rearrange this equation and effectively just integrate twice, okay? So what we'll have is EI times the second derivative of z as a function of position with respect to position squared is going to be equal to our moment of force. So that's just going to be the magnitude of our force. And I'm going to write this as L minus capital X, where this is just telling us where along the length of our beam we are applying our force to give us our moment of force, right? So rearranging this guy, we would have z as a function of x is equal to force divided by EI. And because I've got a second derivative, I'm going to need to integrate twice. So I'm integrating once with respect to x, again with respect to x, and I'm integrating, sorry, this should be lowercase l, minus x prime dx prime dx prime, where I'm using x prime as a dummy variable for position because I have capital X in the limits of my integration. So they're both just, all of that is where along the beam I'm applying my force, okay? And this is a fairly simple integral to do because it's just a first order polynomial and we're integrating it twice. So this comes out to be f divided by EI times the length of the beam times x squared over 2 minus x cubed over 6. Okay. The maximum amount of deflection is going to occur at the tip of the beam. So Z max is going to be equal to Z at L, which simply becomes F times L cubed over 3 EI. And this expression can be rearranged. I guess I can try doing it over here. So F would be 3EI over L cubed times Z of L. And this is going to be equal to KC, our cantilever spring constant, times Z of L, finally giving us a cantilever spring constant. KC is equal to 3EI over length cubed. Our angle of the beam with respect to rest position, theta. So theta as a function of position is the partial derivative of z with respect to position. So this just comes out to be F over EI. Sorry, I drew that line too long. Times LX minus x cubed over 2. And at the end of the beam angle is at its maximum. So theta L is equal to FL squared over twice EI. All right, so during cantilever bending, and I'm going to put a note here, assuming downward deflection, the top surface of the beam is in tension. And let me just write the word "and" out here. The bottom surface of the beam is in compression. So something akin to this, right? So here's the z-axis. This is what's going on close to the anchor point. I think I drew our, axis of symmetry in red earlier, so I'll continue to have that in red. And so what we should see is a stress profile that looks something akin to this. So at the surface, we're at our maximum, and then it linearly decreases down like so. So I'm just going to try to draw a profile like this. Oops, that's on the wrong side of that dashed line. Something like that. So that's our stress profile, where up here we have tensile, good God, stress, and down here we have compressive stress. The longitudinal stress at a location Z, comma X, where I'm trying to remember if we're calling Z is equal to 0, the middle of the beam. That's what I'm trying to look at my notes here. I'll just put distance from beam center. Okay. Is given by T as a function of Z and X is equal to negative M at location X times Z over I. At X is equal to L. This becomes T of let me rewrite that. Sorry, got ahead of myself. So for a point force at X is equal to L, then we have T Z X is equal to negative F of L minus X times Z over I, and maximum stress occurs at the anchor point. So the absolute value of the maximum stress is FLB over twice I, or 3EB over twice L squared Z. Yeah. Okay. We only have like 8 minutes of class left, which is not really enough time to talk about guided beams and all of that kind of stuff. So I feel like this is as good a stopping point as any for today.